This is a 100 microhenry inductor. You've seen this in the previous videos. I just wanted to show you some interesting things here in the DC world before we get back to the AC world. And what I'm going to do is pass some DC current through the inductor, and we see it's also an electromagnet. So it's hard to do everything with one hand here, but I think you can see that this is an electromagnet. Now the core of this inductor is a ferrite material, which is, you can think of it as very fine particles, so there's very little eddy current induction into that core. So this type of inductor is good for medium frequencies. Now, when we're picking up these paper clips, it's obvious there's a force between this inductor and the iron in the paper clips. Of course, it's steel, but steel contains mostly iron. Now, which direction is the magnetic field coming out of this inductor? And let's explore that next, but I need another hand. Okay, here's our inductor again. And what I'm trying to show you is the direction of the winding on the core. And here you can see the wire that's wound around the core connected to the lead here on the end. And I have positive voltage applied to this end. So in terms of conventional current flow, that is not electron flow, but conventional current flow, the current is going to be flowing around the core in this direction. And what I want to show you here is what's called the right-hand rule. And there's many different right-hand rules in the magnetic field area, but this one's for determining the direction of a field, whether it's north or south. So if you curl your fingers around an inductor in the direction of the current flow, your thumb is showing which end the north pole is on. So this should be the north pole end of this inductor when DC current is flowing from left to right. Okay, there's a DC current flowing in this inductor right now, and right here we have a compass, and we can see that the north end of the inductor is attracting the south pole of the compass. So that's what our left hand or our right hand rule told us that it should be. Okay, there's a magnetic field between the inductor and our compass, and we know that there's really no particles being exchanged. At least modern physics doesn't think that gravitons are a particle, but we do know there's a magnetic field, and this should also work in a vacuum as it does here in air, and we know that forces are being exerted through the magnetic field. Now, what about in capacitors? What are the forces in capacitors? Let's take a look at that next. Here's a setup to demonstrate the forces involved with electric fields. We're kind of familiar with magnetic fields due to magnets being readily available. There is a device called an electret, which is a permanent, a device for generating a permanent electric field, but they're very weak and not readily available. So here this is a glass plate, and here I have a piece of aluminum foil bent to stand up, and this is just a piece of steel that's holding the foil in place. Over here is another piece of foil that's bent at an angle, and this piece of aluminum again is just holding the foil down. Now I have an electrical connection to this piece of foil, and it's connected to this high voltage power supply, which generates 15,000 volts. The resistors there are to limit the current. They're 125 megohms each. So this piece of aluminum foil is free to move, so we can show attraction and repulsion between the two pieces of foil. So I'm going to turn on the power supply, and I have this piece of PVC tubing with a wire at the end. And first I'll show you the arc that can be generated. Now as I bring this near here, you can see the foil, the small foil being attracted to the large foil. And notice when it touches, at that point, the voltage on the small piece of foil is discharged, and both pieces of foil are at the same potential, so they repel. So we get kind of a motor action where at first the foil is attracted when they touch or arc over, they are at the same potential and repel each other. So basically we have a capacitor here. The two pieces of foil form a capacitor with an air dielectric between them. And when the foil is free to move, you can see the forces of attraction and repulsion there. Here we have a very crude homemade electroscope, which is nothing but a piece of aluminum foil that is folded in half and hanging from a wire that's attached to the lid of this jar. And we're going to use our high voltage power supply again. And when I bring our probe near the jar, near the lid of the jar, you can see the foil separating because the two pieces of foil are at the same high voltage potential. They repel each other. So the two sides of this foil are essentially a capacitor, but they're shorted together, so each plate is at the same potential. Now if I take the probe away, you can see the charge drains away and the two pieces of foil come together. So this demonstrates that there's a repulsive force between pieces of foil that are at the same potential. We are typically taught that current flow is a flow of electrons, and I'm going to demonstrate to you that that's not necessarily true, and that we can even pass a current through a vacuum or air without any electrons being involved. And what I have here is a metal door, and these are magnets holding some brackets, and hanging from those brackets is a sheet of aluminum. If I can back up here enough, it's 12 inches by 24 inches, which is roughly 30 by 60 centimeters. And it's spaced off of the metal door about 2.5 inches, I would guess. And right here I have two LEDs that are connected back to back, and they are clipped on to that piece of aluminum, and then I have a wire there that I can clip on to pass current through the LEDs. Now here's an oscillator. It's set to 3 megahertz, and that voltage that you see there, that 20 volts, that's peak to peak. So that turns out to be about 7 volts AC, or 7 volts RMS. And that's the maximum this oscillator puts out. So this is hanging from nylon strings, and nylon's a very good insulator. And there's nothing behind there. So let's connect up our oscillator to the LEDs. And there we can see the LEDs have lit up, and it takes current to light an LED. It takes approximately 1 milliamp before you can see these particular LEDs. They're fairly sensitive. But right now, that plate in the metal door is forming a capacitor, and we're passing current through that capacitor. Right now, the dielectric of the capacitor is air, but it wouldn't matter if we did this in outer space in a vacuum. We have current flowing through this capacitor without any electrons being involved. All we have is a changing electric field that's changing polarity at 3 megahertz. Now if we look at the LEDs again, and if I'm going to move the plate closer to the door, and I don't know if you can see them getting brighter. What I'm going to do is turn down the voltage so that they're dimmer. Okay, now the LEDs are fairly dim, and as I move the plate closer, I hope you can see they're getting brighter. There they're fairly bright, and as I move away, they get dimmer. So clearly the capacitance is what is limiting the current flow, but there's no electrons involved until we get into the wires. The current that's flowing across the capacitor is just a changing electric field. And again, it would work the same in a vacuum as it does here with air. So that's current flow without electrons. Just in case you didn't quite get the setup on the door, I've made a schematic here. This plate here represents the door, and this smaller plate here represents the aluminum plate that we had hanging from the brackets. And here are two LEDs back to back, and then this would be our oscillator, which is connected to the door and then connected to the aluminum plate through the LEDs. So when the oscillator goes positive, this LED conducts, and when the oscillator goes negative, the other LED conducts. Now I'll show you a formula here in a minute that shows that our door capacitor was approximately 25 picofarads. And at 3 megahertz, 25 picofarads works out to be 2,000 ohms of capacitive reactance. So that's what's determining how much current is flowing through the LEDs. Now when we move the aluminum plate closer to the door, this number would have got smaller, so the LEDs got even brighter. Okay, this equation here can be used to calculate the capacitance of a simple two-plate capacitor. And the equation is 0.225 times the area of one plate divided by the distance between the plates times the dielectric constant times 10 to the minus 12th farad. Now a microfarad is 10 to the minus 6 farads, and a picofarad is 10 to the minus 12 farads. So basically this equation here, if the area is in square inches and the distance between the plates is in inches, this would work out to be picofarads. Now K is a constant called the dielectric constant, and there's different materials have different dielectric constants. And I'll show you a short table of different dielectric constants. Okay, the dielectric constant of a vacuum is 1 by definition. All the other variables that have to do with electric fields are based on a dielectric constant of 1 for a vacuum. Now air is slightly more than 1, and it varies slightly with the absolute humidity level. Now plastics are in the area of 2 to 3, and that varies with the type of plastic. Oils are sometimes used in high voltage capacitors, and they're in the area of 2 to 5. Glass is in the area of 6 to 10 and varies with the type of glass. Now pure water has a dielectric constant of about 80, and you can make a capacitor with water, and I'll show you that here shortly. Now there's special ceramics that give very high dielectric constants in the area of 200 to 12,000. And it's these ceramics that make possible the very small surface mount chip capacitors. Here we have some real antiques. These are variable capacitors. And at one time you would find something like this in just about every radio receiver that there was. And this is actually a multi-section variable capacitor. Now one set of plates is attached to the rotor, and the other set of plates are stationary. And I think you can see the precision involved in getting these plates to go inside of each other without shorting together. Now this, as you can see, the shaft is off-centered, and the movable plates have a shape to them. And this is to give a constant frequency versus angle effect when this is in a tuned circuit with an inductor. Then some capacitors, it's a linear capacitance with angle. You can see the shaft is centered and of constant shape. The cross-section of the plate doesn't vary with the angle. So it's relatively a constant capacitance with shaft angle. Now the bottom plates are all connected together here, and they're insulated. The rotor assembly is insulated. This is a ceramic insulator on both ends. So the connection to the rotor is here, and the connection to the stator is here. So these are quite expensive to make. I'm sure you can see the precision that's involved. And so circuits were invented so that these were not needed any longer in tuned circuits. The oscillators that these were in were replaced by phase lock loops and other types of circuitry. Also, you might notice the spacing of the plates is different. So as the voltage goes up, the plate spacing has to be further apart to withstand the voltage of the circuit. So we're going to attempt an experiment here. I'm going to make some connections to this capacitor, and then we'll proceed with the experiment. I've made connections to the capacitor and hooked it up to a capacitance meter, and we're showing roughly 95 picofarads. Now that was with the rotor fully meshed with the stator. If we go to 90 degrees, that should be about half the capacitance. And there we're showing 40 picofarads. So that shows how the variable capacitor works. Now the dielectric here is air, and we're going to attempt to change the dielectric and see what happens. I've put the capacitor in a plastic container, and the plates are fully meshed, and we're showing around 95 picofarads. Now what I'm going to do is pour this ordinary vegetable oil that you might put on your salad into the container. just enough to cover the plates of the capacitor. And now we're showing 290 picofarads. So the ratio of those two capacitances is the dielectric constant of the oil. And we can see it's approximately 3. So oil, this particular vegetable oil has a dielectric constant of about 3. Okay, here's our variable capacitor again in a plastic container, and it's reading 95 picofarads again. And now I have ordinary distilled water that I'm going to pour in the cup. Guess you have to take the lid off first. Okay, there the plates are covered, and there we have roughly 8,000 picofarads. Here I've waited a while, and we can see the capacitance is increasing. And what's really going on here is the distilled water is dissolving minerals from the metals and becoming slightly conductive, and that upsets our capacitance meter. But our initial value was around 8,000 or 9,000 picofarads, which would be about right for a dielectric constant of water of roughly 80. Let's get back to inductors. Here I have 2 of those 100 microhenry inductors suspended on nails, and you can see they're connected in series on this end. And I'm going to connect our inductance meter. Okay, that's showing 107 microhenries. And if we move to the other one, we have 104 microhenries. So that the total in series then should be around 210 microhenries. Whoops. And instead we're showing 267 microhenries. So what's going on here? Well, we have something called mutual inductance. And the magnetic field from one inductor is adding to the magnetic field of the other inductor. So now let's connect them in series in the other direction. Okay, instead of the jumper being between the two end terminals, the jumper is now from here to here. So my connection to put these in series will be these two terminals. So let's see what we measure this time. Okay, this time it's only showing 162 microhenries. So the inductance is now less than the sum of the two inductances. So now the fields are combining in a negative manner. So we have mutual inductance can either add or subtract. So you have to be wary when components are near each other, well, when inductors are near each other on a circuit board. Okay, here I've hooked up our oscillator to one of the inductors, and I'm going to take the back-to-back LEDs that we used in the capacitor experiments, and I'm going to connect it to the other inductor. I hope you can see them lighting up there as I make and break the connection. So now in this case, there's no physical contact between the oscillator output and the LEDs. So once again, we're passing current through free space. This would do the same in a vacuum as it is here in air. So mutual inductance can also be considered transformer action. Now, just to show that we weren't passing current between the nails or something like that, here I've connected the LEDs to another inductor. And I hope you can see them lighting when we get close enough to the energized inductor. It's kind of hard, there we go. Kind of hard to show in the bright light here. So again, we're transmitting current and power, in this case, through space. And this is basically the principle of wireless chargers. Here I've hooked our inductance meter up to one of the inductors again to show you something else here. Here I have a couple of strong magnets, and I'm going to bring the magnet near the inductor that's hooked up to the meter. And there you see we went down to 48 microhenries. And we can essentially vary the inductance by how close we get to the core of the inductor. So what we're doing is saturating this ferrite core. There we're down to 35 microhenries at that particular spot. So passing a DC current through this type of inductor tends to saturate the core. So the inductors are rated at so many microhenries at so much DC current. And this magnet is able to generate a field much stronger than is in that ferrite material at the rated current of the inductor. And I believe the rated current for this inductor is 4 amperes. Well, the concept of mutual inductance is taken to extremes in the design of transformers. And in our next video, we'll cover transformers. And there's many different applications of transformers, many different sizes, many different ways to make them. And we'll show you where to get parts to make your own specialty transformers and cover the theory. So be sure to subscribe so you don't miss that one.